Okay, a few people had emailed me questions about some of the applications in your homework. So I actually just picked two applications from section 1.3, and I'm gonna go through them here. I'm probably only gonna do the long form algebra for the first one, and then I'll trust that for the second one, you can all work through the algebra, the Gaussian elimination, and get the answer once you have the setup, because it's probably the setup for the applications that's causing the problem, as the algebra is algebra that you've done before, and this should be more review. It's just the actual setup that can be a challenge. So for the first one, it's actually just number one, because they're all the same. And it says polynomial curve fitting. In exercises 1 through 12, determine the polynomial function whose graph passes through the points, and sketch the graph of the polynomial function showing the points. I'm not going to sketch the graph, we just want to find it. So for number one, we have the points 2, 5, 3, 2, and 4, 5. And we had the rule that said if I have n points, then there's a unique polynomial of degree n minus 1 that goes through those points. So in this case, 3 points, so n is 3. So my polynomial is degree 3 minus 1, 2. So I'm looking for a quadratic, which means I need something that looks like f of x equals a sub 0 plus a sub 1x plus a sub 2x squared. And I just need to find a sub 0, a sub 1, and a sub 2. Now I just need to come up with a system of equations that I can solve. And in this case, I just plug in the points that I'm given to get my equation. So first, when x is 2, I get 5. So I'm going to reverse the order here. A sub 0 plus x is 2, so 2a sub 1 plus x is 2, 2 squared is 4, a sub 2 equals 5. Next equation, x is 3. A sub 0 plus 3a sub 1 plus 3 squared, 9a sub 2 equals 2. And then lastly, x is 4. So a sub 0 plus 4a sub 1 plus 4 squared, 16a sub 2 equals 5. Now I have my three equations, and for the purposes of this, we obviously have different ways to set up and solve this now. For this one, I'll just solve the system of equations out algebraically. Again, ultimately we can do matrices, there's lots of different ways, and we'll keep building on that as we go throughout the semester. But I don't want to kind of solve this problem in a more advanced way now. We want to go along with how the book is solving them. So for right now, you can just solve this algebraically. It's a system of equations. So let's see. First off, solve this one for a sub 0. I get a sub 0 is 5 minus 2a sub 1 minus 4a sub 2. And I'll just set that off right now for when I have to substitute back. Now, plug it into the second equation. So a sub 0, which is 5 minus 2a sub 1 minus 4a sub 2, plus 3a sub 1 plus 9a sub 2 equals 2. Combine everything. Subtract the 5 over. 2 minus 5 is negative 3. Negative 2a sub 1 plus 3a sub 1. 3 minus 2 is just a sub 1. 9a sub 2 minus 4a sub 2 is 5a sub 2. And now clearly I can just solve this for a sub 1. So subtract the 5a sub 2. And now I have an equation for a sub 1. Now take both of those, go into my third equation. A sub 0, which is 5 minus 2a sub 1 minus 4a sub 2. And yes, I'm aware I'm going to have to substitute for that, but we'll do that on the next step. Plus 4a sub 1, which is negative 3 minus 5a sub 2, plus 16a sub 2 equals 5. And now if we look at this, yes, I have to double substitute here to get rid of the a sub 1. So I'll substitute the a sub 1 in and also distribute here. 5 minus 2, negative 3 minus 5a sub 2 minus 4a sub 2 Distribute, 4 times negative 3 is negative 12, 4 times negative 5 is negative 20 a sub 2, plus 16 a sub 2 equals 5. I guess I can combine a little. 5 minus 12 is negative 7. Negative 2 times negative 3 is positive 6. Negative 2 times negative 5 is positive 10 a sub 2. Negative 4 a sub 2, negative 20, that's negative 24 plus 16, which is negative 8 a sub 2, equals 5. Now combine everything. Negative 7 plus 6 is 6 minus 7, negative 1. Then add that over, you get 5 plus 1, which is 6. 10 minus 8 is 2a sub 2. Divide the 2, and I get a sub 2 is 6 divided by 2, which is 3. Now if I substitute that in right there, I get a sub 1 equals negative 3 minus 5 times 3. Negative 5 times 3 is negative 15 minus 3 is negative 18. There's my a sub 1. Now plug both of those in here. A sub 0 is 5 minus 2 times a sub 1, which is negative 18, minus 4 times a sub 2, which is 3. Negative 2 times negative 18 is positive 36, plus 5 is 41, minus 12 is 29. And there's my a sub 0. Now I can go back over here and write out my f of x. F of x is a sub 0, which is 29, plus a sub 1, which is negative 18, so minus 18x, plus a sub 2, which is 3x squared. And it's always good when at the end, 29 minus 18x plus 3x squared, that's the exact same one I got before I did this video. So the algebra checks out. And if you want to check really quickly, I'm not going to take the time to do it, but you can just plug in the points and see if they work. If you plug in 2, 18 times 2 is 36, 29 minus 36 is negative 7, 2 squared is 4, 4 times 3 is 12, 12 minus 7 is 5. You get that point. You can check the other two and you'll see that they work. But there is that, and yes, just so we are clear, you will be doing this polynomial curve fitting. Obviously for homework, it will pop up again on exams and things like that. So we want to make sure we understand how to set up and solve the problems. The other one is one of the current problems using Kirchhoff's laws. And I'm not going to draw the picture. This is problem number 25 on page 33 in your book. And for this one, I'm just going to set it up, and I'm going to trust that all of you can then solve the system of equations, either as a system of equations or using the row echelon form of the matrix, the reduced row echelon form, Gauss-Jordan elimination, you name it. But let's see. For number 25, determine the currents I sub 1, I sub 2, and I sub 3 for the electrical network shown in the figure. So I need I sub 1, I sub 2, and I sub 3. And you have the picture in your book, which I am not going to draw, but Kirchhoff's laws essentially say that the amount of current into a junction has to equal the amount of current out. So first we look at just the I's, and for this one, if you look at the junctions, it looks like I sub 1 and I sub 3 both go into the left, and I sub 2 is the only one coming out, which means I sub 1 plus I sub 3, the two currents coming in, has to equal I sub 2, the one current going out. That gives me one equation. Clearly I need two more. And then the other Kirchhoff's law says that the sum of the currents along a closed path, the sum of the voltage along a closed path has to equal the total voltage of the path, which makes sense. So now I just look along the closed paths. And for number 25, there's one path, say the top rectangle, and another path, the bottom rectangle. For the top path, we have, let's see, I sub 1, then I sub 2, which will give me my closed path. And I multiply the resistance times I sub 1, so I get 4 I sub 1 plus, for I sub 2, resistance is 3 ohms, so 3 I sub 2 has to equal the total voltage for the closed path, which we are told is 3 volts. And then by the same token, for the bottom path, the resistance at I sub 3 is 1 ohm. So 1 times I sub 3, which is just I sub 3. Plus, I'm going to go through I sub 2 again. So 3 I sub 2 has to equal the total voltage of the bottom path, which is 4. Now I have 3 equations, 3 unknowns. I can solve it. Here, just for the setup, I'm going to rearrange it and write it in matrix form. And let's see, if I do that, the top one will become I sub 1 minus I sub 2 plus I sub 3 equals 0, because I want to write my augmented matrix. Then I get 4 I sub 1 plus 3 I sub 2. There's no I sub 3, so that's just 0 equals 3. Here there's no I sub 1, so that's 0. Rearrange this because I sub 2 is first. 3 I sub 2 plus I sub 3, which is just I sub 3, equals 4. Now, drop my I sub 1, I sub 2, and I sub 3, and just write out the matrix. And if I do that, I get 1, negative 1, 1, 0, 4, 3, 0, 3, and 0, 3, 1, 4. And I've done the little dots there. And there's my augmented matrix. And I guess this video isn't too long, so I can run through the reducing here. So let's see. I already have a 1 in the top left, so I need to get rid of the 4 here. So top row and bottom row are going to stay the same. 1, negative 1, 1, 0, 0, 3, 1, 4. Now I'm going to multiply the top row by negative 4. So negative 4 times row 1, and then add it to row 2. Negative 4 times 1 is negative 4 plus 4, which is 0. Negative 4 times negative 1 is positive 4 plus 3 is 7. Negative 4 times 1 is negative 4 plus 0 is negative 4. Negative 4 times 0 is 0 plus 3, which is 3. Now I have that. And in this case, keep changing colors so we can kind of follow along. Now I have a 1 here, and these are both zeros. Now I need to make that a 1. So again, top and bottom will stay the same. 1, negative 1, 1, 0, 0, 3, 1, 4. Multiply the middle row by 1/7 to make that a 1. I get 0, 1, negative 4/7. 3/7. Now, we'll go down here. Leave the top row the same. 1, negative 1, 1, 0. Leave the middle row the same. 0, 1, negative 4/7, 3/7. Now, I'm going to make this a 0 right here, which means I need to multiply this row by negative 3, and then combine it with that row. So, negative 3 times r sub 2 plus r sub 3. and negative 3 times 0 is 0 plus 0, which is 0. Negative 3 times 1 is negative 3 plus 3, which is 0. Negative 3 times negative 4 sevenths is positive 12 sevenths plus 1, which is 7 sevenths. 12 sevenths plus 7 sevenths is 19 sevenths. Negative 3 times 3 sevenths is negative 9 sevenths. 4 is 28 sevenths. 28 sevenths minus 9 sevenths is 19 sevenths. And now, I'm actually just going to stop right here, because now, my bottom row, if I plug in my variables, 19 sevenths I sub 3 equals 19 sevenths, which tells me that I sub 3 equals 1. Now, plug that in here, I get I sub 2 minus 4 sevenths times 1 equals 3 sevenths. Add the 4 sevenths over. 3 sevenths plus 4 sevenths is 7 sevenths, which is 1. I sub 2 equals 1. Now plug in here, I sub 1 minus I sub 2, so minus 1, plus I sub 3, which is 1, equals 0. Negative 1 plus 1 is 0. I get I sub 1 equals 0. And now I have my I sub 1, I sub 2, and I sub 3. And all things being equal, both for this one and the polynomial one, the algebra is pretty straightforward once you have it set up. And even if the Gauss-Jordan elimination is a little bit tricky now because you didn't work with matrices before and you're used to just solving a regular system of equations of substitution or elimination, practice on the Gauss-Jordan elimination. You have enough homework, you'll get a lot of practice on it. But ultimately, the algebra is pretty straightforward and pretty simple. So we do want to understand these applications and their setup, because that's really the only tricky part. Understanding how to create the equations for the different types of problems, whether it's current problems like this, or polynomial problems, or things like that. As I've said before, if there are other questions, examples, homework problems, applications, whatever, that you want me to go over, this is the only class I'm teaching this summer. So feel free to ask, and I will gladly make more videos.